just as we had with our systems with two equations and two variables, we run into special cases when we have multivariable systems as well. So here we have a system of three equations. 1, 2, 3. Equation 2 is already set up for row echelon forms. That's good. In order to get equation 3 in the proper format, we want to have only z. So first, we need to eliminate the x using equation 1, which we can do simply by adding together equations 1 and 3. Equation 1 plus equation 3, x plus negative x is 0, y plus 2y is 3y, negative 3z plus 0 is minus 3z, and negative 1 plus 1 is 0. So we can replace our third equation with 3y minus 3z equals 0. And our next step, again, we want only z in our last variable, so we want to eliminate that 3y, which we can do by adding negative 3 times equation 2. So take negative 3 times equation 2 plus equation 3. So that is negative 3y plus 3z equals 0, plus equation 3, which is 3y minus 3z equals 0. You notice those cancel out, and we're left with 0 equals 0 for our third equation. Now, if we had gotten 0 equals 2 or some other false statement, then the solution would have, then there would have been no solution to the system, remember. But we got 0 equals 0, which is a true statement, but it means that our system does not have a unique solution. There are infinitely many solutions, just as there were when we had our two equation systems. There are infinitely many solutions, but again, they are constrained by the relationships between these variables. So just as we did with our systems of two equations, we say z equals a, and then we plug that in to solve for our other variables in terms of a. If y minus a equals 0, then y is also equal to a. And then we plug those both into our first equation, where we get x plus a minus 3a equals negative 1. A minus 3a is negative 2a. And we add that to the other side to get that x equals 2a minus 1. Therefore, though there are infinitely many solutions, they all have the format 2a minus 1, comma a, comma a. The same result of getting infinitely many solutions will show up if you are given fewer equations than you are variables. So take, for example, the system x minus 2y plus z equals 2, 2x minus y minus z equals 1. In order to get a unique solution for three variables, you need to have three equations, but we only have two equations. We can still do our bit to get this into row echelon form. In order to eliminate the x in our second equation, we want to add negative 2 times that first equation. Negative 2 times equation 1 plus equation 2, which gets us negative 2x plus 4y minus 2z equals negative 4. And to that, we are going to add that second equation, 2x minus y minus z equals 1. Those cancel. 4y minus y is 3y, negative 2z minus z is minus 3z, negative 4 plus 1 is negative 3. And I notice these all have a factor of 3 in them, so I'm going to simplify quickly by dividing that whole equation by 3. So that gets us y minus z equals negative 1. And we can replace equation 2 with y minus z equals negative 1. We don't have a third equation, so we can kind of plug in our own third equation and say z equals a, which is what we use when we do not have a single solution. Then, if z equals a, we have y minus a equals negative 1, so y equals a plus 1, and then we can plug that in to our first equation to get x in terms of a. X minus 2 times a plus 1 plus a equals 2. We need to clear out a little bit of space here. I'm just going to copy this over here so I can have some space to work. And distributing our negative 2, it's us minus 2a minus 2. Negative 2a plus a is, of course, negative a. And then we can add the a and the 2 to the other side to get x equals a plus 4. Now we have all three of our variables in terms of a. So the ordered triple, that is the solution to this system, is a plus 4, a plus 1, and